All right, continuing with our thermo chemistry, basically, we're going to talk about bond entropy. There's an energy that's released when you form bonds and an energy that's absorbed when you make bonds. Okay, so the entropy is associated with breaking 1 mole of any particular bond is called its bond entropy. And we actually have these calculated. There's a chart that you'll have to look at to solve these problems. But they know how much energy it takes, like whatever this is. If this is like chlorine, when you break this bond, it knows how much energy that is released. And same here, this is methane. But now here I'd only do it once. Here I'd have to do it 4 times because there's 4 bonds, hydrogen carbon bonds. So you have to look at how many bonds, and then you can take that number and it's basically you take the energy from the bond, from the reactants compared to the energy of the bond of the products. And when you subtract those two, if you get a negative number, you know it's an exothermic. If you get a positive number, you know it's endothermic. Okay, here's these charts I was telling you about, and I have one of these for you. Again, you'll have to download it. But the bond energy is always positive because energy required to break a chemical, it's how much energy it takes to break a bond. Okay, so if we were doing entropies of other stuff, we might have negative numbers. Okay, but when we're talking about bond entropy, they're positive because it's energy that it takes to break those chemical reactions. Energy is always released when a bond forms between gas elements. Okay, there's always energy released. That never changes. So the greater the bond entropy, the stronger the bond. So if you look on here, if you notice, if you compare carbon, a single bond of oxygen, to a double, look how much stronger the double bond is. This is a much stronger bond than this is, and it takes more energy. So the higher this number is, the stronger the bond. And actually, I think I probably picked the strongest one right there. Okay. So when you compare single bonds to double bonds, here's another example. Just a single bond of oxygen, its entropy is 146. That's how much energy it takes to break that bond. If you're looking at a double bond oxygen, 495. So it's more than double. Okay. So again, when you're looking at bonds, double bonds and triple bonds take much more energy because they're stronger bonds. Okay. All right. So what you do is you add the bond energy from all the bonds made, and you subtract the bond energy from all the bonds broken. Okay. Basically what you do is you compare the reactants to the products. And I have an example to show you in a minute. So I hope I don't totally confuse you by then. Okay. So the result is an estimate of delta H. There are some little things that can, but it's close enough. You know, it's not exact, but it really is close. So it's, when you're looking at the delta H, again, remember that's entropy of a reaction. It's the bond energies of the bonds that are broken, and then the bond enthalpies of the bonds that are formed. Really, it's the reactants versus the products. Okay. Okay. So here's my example. All right. I'm doing a simple reaction because they're easier to type out. And with these, you also have the phases in there. Normally, I don't put those in there because they're kind of a pain. But in these, it's important to know that they're gases. Okay. So what I would do is 2 for hydrogen, and I can go back to the chart, but please take my word for it. If you look for HH, a double bond, 2 hydrogen bonded together, you'll see that its energy is 436. That comes right off the chart. For oxygen, and the chart I give you, I actually put oxygen by itself. This is a double bond O, but I just put O2 equals 495. Okay, so these are the energy from the reactants. Okay, now over here, I have water. Okay, and I put 4 because if you look, there's going to be 2 hydrogen oxygen bonds and 1 mole of water. Okay, because we've got 2 hydrogens, so we've got hydrogen, oxygen, and 1 mole. But since I have 2, there's going to be 4 of those bonds, and I think I even put a little note to that. This is 4 HO bonds because there's 2 moles of water. Okay, in 1 mole there'd be 2, so in 2 moles there'd be 4. So I take 4 times 463, and again, this is an HO bond if you look on that chart. Okay, so then this equals 872 plus 495. That's my reactant side. My product side, if I take 4 times 463, I get 1852. So now what I'm going to do is just going to subtract them. I'm going to take 1367, because that's my reactant side, minus 1852. That's my product side, and this is what it is. So again, when I look at that, is it endothermic or exothermic? It's a negative number. It's exothermic. So energy is released when you take hydrogen and oxygen bonds and combine them to make water. You also, if you wanted to put plus 485 right here, you could. Okay. Or you just change in H's, negative 485. Either or. If it was a positive number, you could write it on this side, or just write delta H's, positive 485. Either way, you know, so if energy is on this side, it's endothermic. On this side, it's exothermic. If it's negative, it's exothermic. If it's positive, it's endothermic. And you guys are probably getting tired of me saying all that stuff, huh? Okay, so what happens with the bond entropies and the entropy of the reaction? You can predict whether a chemical reaction can be exothermic or endothermic just by looking at those numbers. Here's a reaction. We have hydrogen, this must be methane and chlorine bonds. Oh, that's the ones I was showing you. Okay, this is methane, which is CH4 plus chlorine. I was right, it was chlorine. I just went with the green, you know what I'm saying? And so I would take 4 times whatever CH is, and just one of the Cl's. And then over here I'd go, see, now I put a chlorine on here, so I'd have 3 CH and a chlorine, a carbon chlorine bond. And then over here I'd have a hydrogen chlorine bond. And I would add those all together and see what my number was. Okay, and then that would tell me, just like I did before, if it turns out negative, it's exothermic. If it turns out positive, it's endothermic. It's that simple. It's just kind of looking up the numbers and doing your calculations. And I'll show you another one with my little hand videos. I hope those are helping you guys. Okay, energy in foods. Okay, they kind of do it the same way. They look at 1 gram of food and they look at its value, its food value. Now, when you see it listed on your labels, it always says calories, but it's really kilocalories, you guys. But again, from a carbohydrate, this is how much energy gets, 17 kilojoules per gram. Okay. Or if you want to switch it to kilocalories. Okay. Fats, there's much more energy. Okay. Proteins and so on. And then I have some listed. But they basically figured it out the same way. Okay. They took the value. They could do it in a bomb calorimeter to, just burn it and see how much energy, calculating. We talked about specific heat. Or they could do the bonds in the substances. And I think I have one here. Okay, yeah, here you go. If I'm looking for energies in foods, okay, most energy in food comes from carbohydrates. That's our quick energy source. That's why I always say when we're, just dead tired, we have to have a candy bar. Because candy bar is mostly sugar. Sugar is a carbohydrate. Okay. And that's what our main food source is carbohydrates. Unfortunately, we eat too many of those. Okay, but here's an example. This is sugar. This is glucose. This is the simplest sugar. This is the one we want. I mean, if you're in a coma and they only give you one thing, they would give you this because this is what you need. Okay, plus oxygen. You got to burn it. You get carbon dioxide and water. This is a combustion reaction. Okay, and negative 2803. This is the entropy of the reaction. 2,803 kilojoules. That's how much energy is released. And that's what we do when we burn our food. We get energy, we get heat, we get ATP, things like that. Anyway, okay, so we know this is an exothermic reaction. It's going to release heat, which is really important to us because if it doesn't release heat, then, we're going to freeze. Now, when you have fats, you have a lot more energy in fats, okay? Here's a really nice fat there, C57H110O6, big molecule, right? You need 163 moles of oxygen to burn this fat. Imagine balancing this equation. Woohoo! Remember I told you first you do this, so you'd put your 57 here, and then you'd put your 100, your 55 here, and then you'd find out you had an odd number, so you double the first one and get 114 and 210 here, because that'd be, when you add all those up, you get 336. So here we go. It's a combustion reaction on steroids, I guess. But anyway, the thing I wanted to show you is here it takes 6 moles of oxygen. So it's really not hard to burn carbohydrates. Here it takes 163 moles of oxygen. So we can burn our fats. We get a lot more energy from them. Look at the energy here. 2,800, 275,750. I mean, there's so much more energy in fats than there are in carbohydrates. But the reason why we burn our carbohydrates first is it doesn't take much to get them rolling. Like it's like a fire. When you start your fire, first you have the little sticks and you want to get those going. And once they're going good, then you can throw the big log on. You can't start the fire with the big log first because it just won't, you can't get it going. Okay, unless you spray it with all that liquid stuff that starts your barbecue. That's cheating. But anyway, if you take that And you get those, these would be the carbohydrates, would be the little sticks. They're easier to get going. And then once that fire is going, then you burn your fats. That's kind of the premise of like the low carb diets. If you don't have carbohydrates to burn, then your body has to burn the fats. And as long as you're on the low carb diets, you're fine. You know, it'll keep doing that. The problem is it's really easy to get off those diets because, I mean, giving up carbohydrates, you're giving up breads, pastas, our favorite sugars, you know, so they're tough to stay on. But proteins produce about the same as a carbohydrate, but your body really doesn't want to burn proteins. Proteins are for building things, building your muscles, building all that. So your body kind of tries to stay away from proteins and leaves them, you know, leave them alone. But really, this is the difference when you're talking about energies and foods. Here's energies and fuels. We got wood. Anthracite is really heavy coal. In North Dakota, we have bituminous and lignite coal. It's not nearly as good as the anthracite. Here's charcoal. We got crude oil, gasoline, natural gas. Okay, here's the percent carbon, hydrogen, and oxygen, and here's their fuel value. Okay, and you can see wood doesn't have a huge fuel value if you compare it to like natural gas or whatever. But again, these are calculated. And again, for us, we get most of our energy from fossil fuels. You can see coal, natural gas, petroleum. Those are our fossil fuels. We get between 85 to 90% of our fuel. That's why we have a lot of issues with the climate change. Because when you burn fossil fuels, you put extra carbon dioxide in the air. Carbon dioxide in itself isn't a pollutant, but when you get too much, it warms up the earth. Okay? And then other energy sources, one of them is nuclear fission. We don't have a lot of that around us. They have a lot on the West Coast, they have some, and they have some on the East Coast. Other countries, like if you go over to Europe, you will see a lot of nuclear power plants. You'll see a lot of alternative energy because they don't have a choice. They've run out of fossil fuels. Those countries are way, way, way older. We're a couple hundred years old. They're a couple thousand years old. So they've run out of their fossil fuels. Okay. So renewable, and that's what we're pushing for. Solar, wind. I mean, wind is a huge in North Dakota, and geothermal is as well. The college runs on geothermal. It has a geothermal system that helps heat it and cool it. You know, it was expensive to put in, but now, I mean, they gained their money back. It didn't take, I think, I asked one time, it was like 5-6 years. So that's pretty cool. Okay. Wind and geothermal are great in North Dakota. Biomass is burning like this stuff. We're not real good on solar in North Dakota. We don't, in the summer, but what do you do in the winter? But if you lived in California, Arizona, Florida, go with the solar. It can give you a lot more energy, and they're renewable. You won't run out of them. Okay, the video, you guys can watch that. It's on there. Again, after I'm done with this, I'll put this whole PowerPoint without me babbling on it so that you can watch that if you want. It goes through entropy. And again, I'll show you some examples of how to do bond energies in the old hand video. Okay? All right, so that's it for this chapter.